Hello everyone, today we are talking about a new software. It's called Shaft and it's from the softwares of Ensoft. Shaft is one of the softwares that we can use it to define the pairing capacity of the pile, either the shaft capacity or the end bearing capacity with different techniques. So we will look at the software right now and we can see that it's so simple software, but it can do a lot. So here we can find in the main menu, we can find file, data, computations, graphics, window, and help. Here in file, we find that we have new, open, save, and regular things. In data, we can calculate, put like the title of the project. We can control the units if you want English units, pound, feet, inch, or you can if you want kilonewton meter. I prefer to use SI units, so I'm gonna check it. Here we can define the method of analysis if you want allowable stress design or load design, factor design, and we will see the difference between both of them. Then we have here drilled shaft properties where you can define the properties of the shaft and we will look at it. And we have soil layer where you can put your layer and we will see this in details. And then we have the factor of safety if you want to include a factor of safety. And here is the computational method if you want to specify the shaft length or to specify the load. And here is the water table and here is evaluating multiple shaft lengths if you want to show different lengths. And here some charts and we're gonna see this in details in a minute. And this is the controlling option and here the printing and the increment of the depth of the pile. In the computational, after you run your analysis, we can process this. And this is the graphic. This is the things that we can view, which is the ultimate skin friction versus depth, ultimate tip resistance versus depth, ultimate total resistance, and combined plots. And here some other graphs, and we're gonna look at them in details. Here is the axial load versus displacement, average and upper limit and lower limit, and combined between them we can also view the TC curve and QW curves and other curves. So let's take an example and let's start to see the end bearing capacity or the bearing capacity of the pile. As we can see here, we also can do the same thing as from data from here. Here, this is the title of the project, and here is the soil, and here is the shaft. So for the minimum, as we can see here, this is the description, and as we can see in the graph here, we can find that every one of these is described here. So for the minimum shaft diameter B, as we can see here, we can say that we have a shaft diameter of 1 meter, and the maximum shaft diameter B to be considered. So we're gonna include it as the same of B here. And the ratio of the base here, QB, we will consider it 1 because we will consider if you want to increase the base here or to keep it as the same, because if we increase the base here, that will increase the tip resistance. But in our example, we will consider a uniform pile or a uniform shaft. So we will add it the ratio between here like B and PP and P will be 1. The angle will be 0, so we have no angle. And also, so the angle will be 0. And as he suggests here, enter 0 for straight shaft. And length of upper extension zone LU, this one, we consider it 0 also. Um, if you want to consider it like the length of upper extension without skin friction, like if you want to ignore like part from the skin friction, if the pile, like if you don't want to include it, so I will include the skin friction from the whole soil, so I will not add anything. And as we can see here, the length of the bottom portion of the shaft without skin friction here, and I will consider it 0. I want to include the skin friction at this part also. And finally, the modulus of elasticity of the drill shaft, either if it's gonna be like a concrete shaft or if it's gonna be a steel shaft. For this example, I'm using a concrete, which is gonna be 2.1 E7 kilonewton per meter square, or kBA or kilopascal. So this is for the shaft parameters. Then I will go here to the soil parameters. At the soil parameters, we will find that here is the layer, and here is the type of the soil, and here is the depth at bottom, and this is the maximum site friction if you want to consider something. As you can see, the software is giving you some tips here. So he says, for example, depth at bottom. This is a description for this. He says here, bottom of last layer must be deeper than a shaft bottom plus 2 pile diameter. So it says that like the length of the soil, it should be greater than the length of the pile plus 2 times the diameter of the pile. So if we having a pile and the pile length will be 10 meters length, so the minimum depth of the soil we have to, or the soil section we should include is 12 meters. Also, for the maximum site friction, if entries are left as 0, the program assumes no limitation for this, because there are some codes which define the maximum skin friction for the pile. But in our example, we are not gonna include any limitation for either the maximum for the side friction or for the end bearing. For the end bearing, use a very small number like this for layer where load transfer should be ignored. So if you are like counting for the end bearing at a specific layer, or you don't want to include the end bearing, you can add it as 0. So for this example, we are not gonna put any limitation, and I will start to consider sand layer, or let's start with, as we can see here, this is the soil types. We can consider sand from the FHWA, or we can consider shale from Reese and Aurora, and strong rock or weak rock, strong rock from which has side friction and end bearing, gravelly sand or gravel. For this example, I will start with a layer of clay, and depth at bottom, I will say the depth will be like 5 meter, or let's say 6 meter. Then I will add another layer which will be sand, and it will be, let's say, 10 meter. So if we entered here to the specs of the clay, you will ask for some description. First thing, you'll ask for the total unit weight. So the total unit weight here will be, let's say 16, and let's say it will increase till 17. That means that the value at the top, let's say it's gonna be 15 at the top, and it will increase through the 6 meter to, let's say, 16. And the cohesion of the clay, we can say here that the cohesion of the clay will be 25, and it will increase up to 35. As we can see here, he's asking for the count of SPT and the alpha factor and the bearing capacity factor NC. So here for the first one, he's saying program will ignore blue count value if cohesion is defined. So it's either you define the cohesion or you define the SPT. The program has embedded equation which transfers the SPT equation numbers into a cohesion. Also, for the alpha factor and the bearing capacity coefficient in C, if you remember from the bearing capacity equation, you also, as you can see here, the program will generate initially the value if it's left 0. So if you have a limitation according to a code for the alpha method or the bearing capacity coefficient, because we know that from for the clay, the friction will be, or the equation of the bearing capacity of the bar, it will be the part of the end bearing and the part of the friction. So the part of the friction can be related to an alpha method, which will be you multiply or reduce the cohesion by a factor alpha, and you multiply this factor by the overburdening pressure. And for the part of NC, it comes from curves, and it depend on the angle of internal friction. But the program says that if you left these values 0, he already has embedded curves which will be used to do this. We can see in future videos the details of how this software calculates this. But for now we will include, like, we will leave them 0 and we will let the program to calculate them. For the sand layer, as we can see here, there are different methods for calculating the sand. There is the K-node method, which is the static method where you define uh, 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 where you can just calculate from the lateral pressure, the overburden pressure multiplied by K node, which at least earth pressure coefficient. And either you can use beta method where you can define beta, which is a factor you can obtain it from the codes or from codes, and we can talk about this in details later. Or you can include Chen and Kulhawi 2002 method. For this example, I'm just using the K-node method, and for the total unit weight, I will say it will start from 16.5 and it will go up to 17.5. For the coefficient of lateral earth pressure, K node equal 1 minus sine phi. So let's say if we have the angle of internal friction, here, as we can see here, we either include the SPT or the angle of internal friction here. Say the program will estimate the friction angle based on the blue if it's left 0. So for me, I will either you include the SPT numbers or you can include the friction angle. Here we can say, for example, we are going to include the SPT number. Let's say we have 44 blow at the top and it reached to 50 at the end of the layer. So for the K node, it's 1 sine phi. So let's say it's roughly, K node, it can depend on the Poisson ratio or it can depend on the angle of internal friction. But let's say as assumption, and we can talk about how we can calculate K node in details in another video. So for this example, we assume that the angle of internal friction will be 30 and it will increase to 35. So it's going to be 1 minus sine phi, which will be half, and it will increase to 1 minus sine 35, which will be 0.42, because with increasing the angle of internal friction, we know that the coefficient of at least earth pressure will decrease. So let's say it will decrease up to 0.43. And I will say close. Now I define my parameter and I will say close. If I came here, I would see, sorry, if I came now to the factor of safety, this is the factor of safety applied for the side friction. I will keep it 3. And for the ultimate base capacity, I will keep it also 3. Here, view soil. So this is my soil here. And this is the layer 1. And this is layer 2 with depth 10 meters. And for 3D view, as we can see here, this is my problem. Now I have to go to data now, and I have to design it to choose. Either choose allowable stress design or load resistance factor design. And for drill shaft, we already choose this, and soil parameter we choose this, and computational method. Do you want to specify the shaft length or to specify the load, the design load? If I specify the design load, he will ask me. Sorry, if I want to specify the pile length, so I will assume that the pile length here is 10 meters. I can change it, and the type of loading is compression. So it's important here, either you put the load and see the length, or to put the length and see the load. Then I will go now to water level. So I assume that the water level is 0. Let's say, as we can see here from the 3D example here, that the water table is at the top. But if I change it, the water table here, to be, let's say, -3, -3, and I said okay, and I show it here. Sorry, so it's gonna be 3, and I said okay, and I show here the 3D. We can see that the water table has decreased until here. So now all I have to do is to run my software. It will ask me to save it, so I'm gonna save it here. Shaft, and we call it project 1. He say depths of bottom layer 10 should be at least of the shaft plus 2 times. I say okay. So if I went back here, he says this is the depth. So that's not the thickness. We did a mistake. We choose the depth of the soil to the pile to be 10 meter. However, we choose the depth of the layer to be up to 10. We have to differentiate between the depth and the thickness, so that we will increase this to be 15. And I say, or sometimes some could say up to 4 times, 5 times, 6 times, so let's say up to 20. And I say close. Now when I start to run, he say computations are complete, and I say close. So now I can start to see my graphs. As we can see here in this graph, we can see that the first graph here is the skin friction. So the skin friction start to increase gradually until we reach to depth 10 meter. However, here the bearing capacity, as we can see, it increased until here. So if we want to see what these graphs mean, this graph means that at depths, let's say 2 meter, the capacity of the pile, including if the pile stopped at 2 meter, so this is the shaft capacity plus the end bearing capacity, so the total capacity will be 3 meter. But we have to understand this is the ultimate axial capacity, so this capacity is not yet divided by the factor of safety. So the ultimate capacity, it's gonna be around, let's say, 300 kilonewton. But if the shaft length is 6 meters, that means that the since we have been now in the sand layer, that means that the sand layers end bearing is very large. So the end bearing force has increased tremendously, and the end bearing only it's 1500 kilonewton, while the shaft resistance it's still at 3, and the total resistance will be at depth 6 meter will be 1800 kilonewton. And if we looked at here at this combined plot, we find that now it is divided by the factor of safety, and at 6 meters we can see that it's 600, which makes sense, which divided the 1800 by 3 and it becomes 600. So this is the curve for the axial load versus the displacement. So from this curve we can define the load. If the axial load on the pile 1500, that means that the settlement versus this will be um, almost 1 centimeter. And if we increase the axial load up to 2800 kilonewton, that means that the settlement will increase up to 5 meter. So we can see that this graph or this software is very efficient to calculate the bearing capacity of the pile. We also can calculate the TZ curve here. We can see that this is for H 0.3, 1.73 up to H 20 meters. So we can see this is the ultimate load transfer. Like this is the shaft friction, like the shaft friction versus the axial displacement. Because we know that the TZ curve, T is the shaft friction versus the axial displacement. And we can also see the bearing curve, which is Q versus settlement. We can see that it increased at for the diameter 1 meter. We can see this is the curve, this is the tip load, and this is the displacement versus this load. So if we went here to graphs, we see that we already viewed everything. We can also here view um, we can see here the axial load versus displacement average. We can see the upper boundary. We can see the lower boundaries. We can see combined all of them, the upper boundary and the lower boundary and the average. We the same for the skin friction, the same for the tip resistance and total resistance, and all of them together. And this is the factor of safety divided by the factor of safety. This is the same as this, but this without the factor of safety. This is the ultimate values. This is divided limit state values divided by the factor of safety. This is axial load versus the settlement, and the average, the upper, the lower, and all of them. And this is the T curve, and this is the QZ curve. So let's say if we went here to data again and we went to the computational method. Now we define the shaft length. This time we'll define the design load. So if I want to design a pile length and to carry a capacity up to 1000 meter, well, 1000 kilonewton, and I started to run my analysis, and I went here to the allowable. So I find that in order to obtain a full capacity of 1000 kilonewton, I have to have a pile length up to 11 meter. And the pile settlement here at 1000 kilonewton, it will be 5 millimeters. And also we can find the QZ and TZ and other curves. You can change here the control, and you can change the increment of the calculation. Here for me, I choose increment of calculation, or by default in the software it chooses it to be 1 feet, which is 0.3. You can change it if you want, and here where you can save your text, and also you can go here and you can export all your results into Excel. So this is the software. It's very simple. As we can see, you can calculate and you can design the bearing capacity of the pile. So easy.